Okay, hi everyone. My name is Ananth. Today I'll be talking about tsunami propagation into coastal rivers. So I'm a postdoc at University of Queensland in this reef restoration and adaptation program. So in this project we are trying to look at restoring Great Barrier Reef and looking at hydrodynamics responsible for generation of coral rubble. Sorry, I hear someone. So I started in this position 6 months ago. So I've been working in this project. And today, the topic I'm talking about is from my PhD thesis on tsunami propagation. So in this presentation, I want to give a background of tsunami research because I think many of us may not be from the same research background as me. So it is helpful for others to know the background and tsunami research. And then I'll talk about tsunami propagation in rivers. And if we have time, then we'll look at erosion around bridge piers during tsunami propagation. So looking at the background, a tsunami is usually generated when we have disturbances underwater. So it could be an earthquake or a landslide or an volcanic eruption underwater. That is going to generate a disturbance or a very long wave that would then propagate towards the beaches or shores. And when the wave is traveling towards the beaches, we see that the we see that the water depth that is very large initially in the ocean, in the deep ocean, that becomes smaller and smaller towards the beach. So because we have certain energy coming through the wave, to conserve the energy, the wave height would increase because the water depth is decreasing. And this process is called shoaling. And usually it can be predicted using Green's law, where if we know the offshore water depth and the water depth at a location on the beach, then we can estimate what would be the wave height close to the beach. And in the case of a tsunami, it can reach sometimes up to 40 meters. For example, in 2011, some of the waves were reported to be 35 meters or 40 meters high. And these are two examples of a tsunami. On the left-hand side is a tsunami that is generated due to an earthquake underwater in 2011 close to Japan. And that is by far the biggest tsunami in Japan. And on the right-hand side, we see an earthquake that happened at Indonesia. Even though the earthquake epicenter was on land, opposed to here where it was underwater, there was tsunami close to Palu region. So that was because of this earthquake, there were a lot of landslides along this bay area, and those landslides created some large waves. So that tsunami waves impacted this Palu region a lot. So this was very recent in 2018. And to mitigate or protect from tsunami, we usually have two approaches. One is to have early warning of tsunamis, and then other is to build some structures such as seawalls. This is a tsunami dot buoy, which is going to record tsunami waves if there's an earthquake. This is deployed. So we have a number of these buoys deployed across the oceans, and these would detect if there is any earthquake. These would detect the tsunami waves and then send back the signal to the tsunami warning centers, where we process the data and issue tsunami warnings depending on the wave heights. And this is a flow chart of how the tsunami early warning works. The early warning centers usually have pre-computed tsunami wave heights for different scenarios of earthquakes, landslides, and other things. And if there is an earthquake, we look up from the lookup table and see if there's a possible tsunami with this earthquake. And if there is indeed a possibility of tsunami, then we look for the real-time data from the dot buoys to confirm the tsunami. And depending on the wave height that we observe from the dot buoys, then we issue a tsunami warning. If the wave heights are too small, then even though the tsunami warnings are issued, they would be recalled. And when we look at the second strategy of building structures to prevent damages due to tsunami, we consider two important parameters. One is run-up and the other is overtopping, which I'll be talking on later. The run-up is the vertical elevation the tsunami wave can reach. So for example, on the left-hand side, we see a tsunami wave in the deep water that comes towards the shore and it's increasing in wave height. And this increase in wave height can make the wave reach up to higher elevations. So for example, in this video, if you can see. So on the video on the right-hand side, you will see a solitary wave, which I'll talk about later, that is representing a tsunami that is going up a beach. And R represents the vertical elevation from the mean sea level, and R is our run-up parameter. The second parameter is overtopping. Overtopping is simply the amount of volume or the volume of water that goes on top of a seawall, for example, or any coastal protection structure. That is overtopping. And if we know how much water is going to go on top of the structure, then we can revise the design of the structures based on the overtopping data. And usually in the lab, to quantify either run-up or overtopping, solitary waves were used as representative tsunami waves. This is because in the earlier studies, maybe in the 1970s, there was experimental studies where they generated some disturbance underwater and observed what waves would evolve. And they observed most of the times that if you have any disturbance underwater, that would transform to a solitary wave. This solitary wave is unique because when it is traveling in a still water of constant depth, it is going to travel with the same shape without change in wave height. And once it gets to the beach, it's going to show according to Green's law. And this is quite simple to represent just based on the wave height and the water depth. And so there are some experimental studies that looked at overtopping volumes as well as run-up on plain beaches. It was found that the run-up relation, so the run-up, which is on the y-axis, increases with the wave height, which is quite straightforward. And the overtopping volume, which is the volume on top of the beach, is directly proportional to the deficit in freeboard, so which is R minus Z here in this case. And for example, if the beach is truncated at still water level, then we would see that 20% of the wave volume would overtop the beach. Then there is a debate about using solitary wave as a tsunami wave. This is because when we look at the previous experimental studies, people just generate a solitary wave and derive results of overtopping or run-up, and then they extrapolate these lab results to field scale. But there is a debate whether we should be using solitary wave or not. That is, if we look back at this particular study by Matson in 2008, which is quite popular, they did some numerical modeling with some initial disturbance. Let's say this is a rectangular disturbance. And then they looked at if this disturbance would evolve into solitary waves or not. So if we see here with time, we see that the disturbance does evolve into the separate solitary waves, but it takes much longer distance than what we have around the Earth. So for example, they say for this solitary wave to evolve from this shape, the wave has to go around the Earth at least twice or 3 times, but we don't have that distance to cover. So solitary wave is quite unrealistic to use as a tsunami wave. And they also say if we have a wave of this form initially, then there might be some undulations developing on top of the wave. If we look closer at the wave, we see that there are some undulations, but below these undulations is the big wave. So this is the wave volume that is traveling beneath these undulations. This is what was observed in 2004 in the Indonesia tsunami. So these undulations on top of this big wave. If you're looking from the beach, you just see some short waves coming to you, but in reality, there is huge volume of water that is coming towards you underneath these undulations. So even though it might just look like a series of waves, there is huge amount of volume as it's shown here. So that's a tremendous amount of volume coming towards the beach, even though it appears like it's just small series of waves. So that was a background of tsunami research, what people have been focusing on. And the key points being run-up and overtopping are important parameters in designing structures. And use of a solitary wave is only an approximation to tsunami wave, but not a true representation of tsunami wave when we want to look at overtopping on beaches. So now I want to talk about tsunami propagation in rivers, which is a part of my PhD thesis. The first question is why to study tsunami propagation into rivers. So on the left-hand side, we see a picture from Japan. There was a river going through this city, and there was a mountain here. When the earthquake and tsunami happened, people living behind this mountain, they thought they were safe from tsunami because they cannot directly see the ocean, and they thought the ocean waves cannot reach them. But unfortunately, the tsunami entered into the river, and it traveled along the river on top of the river flow, and it inundated this region as well. And on the right-hand side, you see an example picture of tsunami wave going into the river and overtopping the river bank. So this prompted me to do further research on this because not many people studied this phenomena. And if you want to look at field data, because tsunami waves have high energy, whatever the wave gauges are along this river, most of the places they are destroyed. So we don't have much data from the field as well. So in my research, I did experiments replicating this field scenario in an idealized scenario in the lab. And this is another example of tsunami inundation along different rivers on east coast of Japan. So here we see that on the coast, the inundation is only up to this level, which may be 2 or 3 kilometers, but the tsunami waves can really go up to 20 kilometers, or in some cases, it was reported to travel up to 50 kilometers and inundate the adjacent areas. So this really poses a threat, and not much research has been done on this scenario. Once a tsunami wave enters a river, it's not going to travel as a wave itself, but it's going to transform into something called a bore, or this is also similar to a moving hydraulic jump or a tidal bore. These are two examples of the bores shown, one from 1986 and other from 2011. We see the bores are traveling up the river, whereas on the adjacent lands, we see there is no flow of tsunami. And this is the water level signal from one of the tide gauges, some of the tide gauges in one of the river. So mainly the feature in this signal is that the tsunami is not just one wave, but it has transformed into multiple waves in the river. So that's why we see, I think there are 10 to 11 waves in this river. And another distinctive feature is that we see this abrupt rise in the water level, or a discontinuity, so representing a bore. And we need to model this in the lab. Apart from the experiments which I'll be talking about, I also did some numerical modeling to see if the numerical models that we currently have in tsunami warning centers can issue correct tsunami warning if there is a tsunami wave going up a river. Usually these models are validated against these benchmark cases. So one is a simple case where the wave is just going up a plain beach. The second case is it's going up a complex beach. And then we have some 3D scenarios where we look at the wave transformations. But there's no data set where the model needs to be validated against for tsunami in rivers. So that's why.
Power off.
I'm sorry about that. So that's why I did some experiments in the lab. So this is the wave flume that we have at UQ, where we have wave maker on one end, and then we have a wave absorber on the other end. And we are looking at plan view. So let's say this is a river wall that is going from one side of the flume to other side. That is 20 centimeters in height. So once the wave is going towards the end of the river wall, then the wave would be overtopping into these small compartments. So these compartments are just made by PVC sheets from the supporting sidewall. So we collect overtopping volumes per meter length of the river wall and use this data for comparing with the numerical model. And we measure the wave heights along every 1 meter in the convergence, and also we measure the overtopping volumes. These are the test conditions that I did. So we have 3 different still water depths. Each water depth has different wave heights and different bores. Bores are generated as breaking solitary waves. So here, whereas here, these are non-breaking waves. And as you can see, for bores, I define it as 3 strengths: weak, moderate, and strong. So weak is when the wave maker is moving only 50% of its stroke length, whereas the strong bore is when the wave maker is moving 100% of its stroke length. So we use these kind of bores for all 3 different water depths. So this is what it looks like in real life. So this is the river wall that is going from one side to the other side. And we have compartments behind the river wall to collect the overtopping volumes. And here we see a solitary wave that is going towards the end of the convergence and overtopping the river wall. And these are some videos of the experiments. So on the left-hand side, you see the wave has not overtopped in the beginning because the wave height was smaller than the wall height. So it just goes without any overtopping. Whereas on the right-hand side, you see there is overtopping from the beginning because the wave height was higher than the river wall height. And the 2 models that I used, of course, I used both 2D and 3D models, whereas here I'm just talking about 2D models. So I used 2D models, Anuga and basement. Both of them are based on shallow water equations without any turbulence. And they have some assumptions like the fluid is inviscid and incompressible. And these models are generally validated when the wave height to water depth ratio is 0.2 or less than 0.2. Whereas in my experiments, the ratio was more than 0.2, because in rivers, it's not always less than 0.2, but it can be more than 1 as well, as opposed to on beach where the ratio might be smaller. So in both Anuga and basement, the domain configuration is similar to the experiments where we have the wall and then dividing compartments. So these are some results from both experiments and modeling. So the black lines represent the experimental measurements of the solitary wave in a straight channel without any convergence. So in this case, we don't have any convergence or no overtopping. So this is our reference case. So in this reference case, we see the solitary wave is just propagating without change in the shape and just a slight change in the wave height. Whereas in the model, we see that the wave heights decrease very rapidly. And we also see the waves steepening here. So that is because the crest of the wave is trying to propagate faster than the other parts of the wave. So that's why we see the waves steepening, and then with some numerical diffusion, we see the wave heights decaying rapidly compared to our experiments. And now when we look at the convergence, in the convergence, because the width of the channel is reducing, the energy has to be conserved, so the wave height is increasing. And then once the wave reaches a certain limit, it's going to break and then reduce in wave height. Whereas in these models, both Anuga and basement, we see the wave heights decrease initially and then gradually show up towards the end of the channel. So here, if the wave height is always under predicted than experiments, then we would not see any overtopping on top of the river wall. And this is a case of a bore or a breaking solitary wave, where we see the overtopping is happening from the beginning towards the end of the channel, because the bore height was much higher than the wall height. And yeah, so I try to model this in the Anuga and basement as well. And in the first case, without any overtopping in a straight channel, we see that in the experiments, the bore height remains more or less constant. Of course, there is some dispersion happening behind the wave. Whereas in the numerical model, we see the wave heights decrease quite rapidly, similar to solitary waves. So this is because of the numerical diffusion. And then when we put in the convergence, as I said earlier, the waves are going to shoal in the convergence. So that's what we see in the experiments. Whereas in the model, the wave heights reduce and then increase. So the models do not capture the wave, neither the wave shape nor the wave heights properly. And looking at the overtopping volumes, so here I'm showing the overtopping volumes for a bore. The markers are the peak wave height. From the experiments, we see the wave height increases, or more or less it's an increasing trend. Whereas in the modeling, we see the wave heights decrease initially and then they gradually increase. And looking at the overtopping volumes, we see the models do not predict any overtopping volume in the first 7 compartments. And they only predict overtopping volume in the last 2 compartments. So the models are not doing anything good here in terms of predicting tsunami wave height or tsunami overtopping volumes. So these are the key findings from this modeling, that when solitary waves and bores propagate into the convergence, they're gonna steepen or increase in wave height. And then the behavior of waves, non-breaking waves, is different from breaking waves. The nonlinear shallow water equations cannot capture the phenomena that we see in the lab. And the overtopping volumes were highly underestimated in these 2D shallow water equation models. So I did further modeling with 3D models, which I'm not showing it here. And the next thing I want to talk about is erosion around bridge piers when the tsunami wave is propagating. So previously I discussed at a macro scale where we are looking at inundation in terms of in terms of kilometers length or tens of kilometers length. Whereas now we will be looking at a very close-up view of what's happening around a bridge pier when the tsunami wave is propagating. So this is a kind of a micro scale understanding of what's happening around the bridge pier. Usually for a steady flow, we know what the flow phenomenon is around the bridge pier. So it's going to form a horseshoe vortex, and behind the pier, there's going to be a wake vortex. The horseshoe vortex is going to create erosion or scar around the pier. But we are not sure if this is the scenario for highly unsteady flows like tsunami flows. So I did some experiments to validate or verify this theory of steady flow current in case of not unsteady flows. And so these are some pictures of bridge failures or damages during the 2011 tsunami, where the field reports, they mentioned that these piers were damaged due to erosion around them, whereas here the bridge was damaged due to impact rather than erosion. So there could be two factors acting to cause failure of the bridges, either erosion or impact. And here I'm looking at erosion. And this around this bridge, there is a story that there was a school next to the bridge. And when the tsunami happened, the teachers thought they might be safe on top of the bridge, and they evacuated to the top of the bridge. But the tsunami waves being high energy waves, they impacted the bridge and they destroyed the bridge. So that was a sad story. These are the bore surface elevations and velocity signals that I used to measure erosion around the piers. These are again the same strong, moderate, and weak bores based on the stroke length of the wave maker. And this is what the wave surface elevation and the velocities look like for this case. And earlier, so this is what it looks like in the experimental setup in the wave flume. So this is the pier model. And then we generated a solitary bore, which is the breaking solitary wave that is traveling towards the pier. And I measured velocities around this pier to try to understand if there is any horseshoe vortex formation. And then we also have some experiments with sediment bed looking at erosion patterns around the pier. On the left-hand side is the experiments where I measured surface elevations and velocities using the ADV. And on the right-hand side is a sediment bed, just 1 meter test section of sediment to observe the scour patterns rather than observing or quantifying maximum scour depth. So we just wanted to see the scour patterns here. And we used the similar solitary bores as I explained before. And these two pictures show when the bore is impacting the pier. And this is behind the pier. Here we see the flow is diverging from the pier on the sides, and then it merges again behind the pier, causing a vortex. And this is from the top view. Sorry. So here we see some vortices forming, and the merging of the flow behind this pier is usually termed as a rooster tail in the literature, particularly for this scenario of breaking waves. So this is termed as a rooster tail behind the pier. And looking from the side view of flow around the pier, we are mainly interested in velocities in the vertical plane, what's happening here. And this is from the ADV measurements of velocities, looking in the 2D plane. So with depth, we are looking velocity vectors. Initially, when the bore is just at the pier, we see the velocities are all uniform in the horizontal direction. So there is some downward flow, but not very significant. Whereas once the bore front has gone past the pier, we see the flow is going towards the down. And then behind the pier, we see some vortices. And this is indicating some tendency to form a horseshoe vortex. And we have a wake vortex behind the pier. And once we put in the sediment bed, we try to observe the scour pattern and also the scour process, if it would form a horseshoe vortex. So So from this video, our observation was that initially the sediments were picked up from the sides, and then later on it would start eroding from the front. That's because, as I said earlier, initially the velocities are all uniform in the horizontal, whereas later on we might see horseshoe vortex forming. So that's when the scar on the front starts. But there were some concerns about this experiment because if we remember from previous slides, I showed the bridge piers were damaged due to tsunami waves, whereas in our experiments, we were not seeing erosion to the bottom of the flume, which is only 2 centimeters thick. So if we do not see the bottom of the floor, then it is saying that there are some scale effects happening in our model, which needed to be addressed. And looking at some scaling calculations very quickly. So we see in these experiments, the time scale was 1 in 450 and our depth scale was 1 in 25. So based on the depth scale, our required time scale was 1 in 5. So our required time scale was 1 in 5, but we were getting time scale of 1 in 450. So we had to do some new experiments to rectify the time scale so that we can reduce the time scaling effects. To address this scaling effects, I did some experiments in the long channel where we have a reservoir of water and then some tailwater. If we suddenly release this gate, then it is going to form a bore that is similar to a breaking wave or a tsunami wave, and that replicates what we did in the wave flume tank. And to get rid of the time scale effects, we created a longer duration wave so that the time scale effects are reduced. Here, what we do is first we release the reservoir and then we maintain the same discharge as what we get for a dam break flow to achieve a total duration of 270 seconds or 300 seconds to eliminate the time scale effects. And similarly, we have the pier model of same diameter. And this is what the surface elevation and the velocity looks like in the new experiments. So the bore was initially 30 seconds long, and then behind this, we would have certain discharge to maintain the bore going on so that we have longer duration of a breaking wave. If we have longer wave, then we see that the time scale here, initially it was 1 in 400, 1 in 450. It has reduced to 1 in 6, so which was what we needed to achieve to observe the actual scar results. And I'm not sure if this is clear, but I'll try to play this. Yeah, I think it's all pixelated, but this video is just observing scar around the breaking wave, under the breaking wave. And of course, I measured the bed levels around the pier to plot the surface bed levels. So TW1 to TW6 represent 6 tsunami waves, one after the other. If you remember from earlier slides, I showed the water level in the Japan River. There were multiple tsunami waves, not just one. To replicate that, we also did 6 waves of tsunami, and the erosion in the first wave was much rapid than the second or up to 6 waves. So initially the bed level was here at 0. Just after the first wave, it dropped close to 2, -2, and then it dropped to -2.5. So this is elevation non-dimensionalized with diameter of the pier. And this is what the scar hole looks like in the experiment. And this is the bed levels measured and contours plotted around the pier, with the scar closest to the pier being the highest, that is 2.5 times the diameter of this pier. If we compare that with steady flow estimations from empirical equations, usually is a design discharge is, if we compare with the tsunami discharge, a design discharge is maybe 30% of only 30% of tsunami discharge. And using empirical steady flow equations, we estimate the scar depth to be 65% of tsunami scar depth. So we are underestimating scour depth by 40% if we neglect the tsunami discharge. And the main concern, the main point here is that a steady flow to achieve its maximum scour depth, it would need 30 days or 60 days in the field, whereas tsunami has a duration of only 6 hours or maximum of 12 hours. But still you see higher scour than a steady flow. And the key learnings from this study were that a horseshoe vortex would form behind the bore front rather than during the total duration of the bore. And this horseshoe vortex is responsible for erosion. And before the horseshoe vortex formation, the flow accelerates around the pier and picks up sediments on the sides. And later on, the horseshoe vortex would pick up sediments from the front of the pier. And previous studies, as I showed in the last slide, the previous studies underestimated scour depth by 40% sometimes, or even 60%. So from my study, the key point is that the maximum scour depth due to tsunami can be 2.5 times the diameter of the pier, which is much higher than steady flow scour. And scale effects are definitely important when we want to design experiments, particularly with sediment, and we need to be quite careful about this. And this is my last slide, where Japan is now considering to build a wall along east coast of Japan to prevent the tsunamis. And they call it the Great Wall of Japan, which is 14 meters high above the ground and 25 meters deep below the ground, which might have huge environmental impacts, which I have not read about it yet. But this might be the future of Japan and what they might be doing in the coming years. Thank you.